At the smallest conceivable scale of reality, the Planck length, a distance so infinitesimal that if an atom were the size of the known universe, the Planck length would be the height of a single tree. Space-time ceases to be the smooth geometric fabric described by Einstein. Down here, at 1.6 times 10 to the 35 meters, our classical intuition shatters completely. According to quantum field theory, the universe at this resolution is not calm. It is a violent, chaotic, seething cauldron of energy. Across every cubic centimeter of the cosmos, in the space between the atoms in your hand and the void between galaxies, a process of unimaginable intensity is underway. This is the realm of quantum foam, a term coined by the legendary physicist John Wheeler to describe the very texture of space-time when quantum effects dominate. Here, reality is forged and unmade on timescales so brief they defy comprehension, at a rate estimated to be 10 to the 100 times every second. This isn't a metaphor. It is the direct mathematical consequence of our most successful physical theories. The origin of this cosmic storm lies in the fusion of two of the 20th century's greatest ideas, quantum mechanics and special relativity. Quantum mechanics introduced the world to the Heisenberg Uncertainty Principle, a fundamental rule stating that certain pairs of properties, like a particle's position and momentum, cannot be simultaneously known with perfect accuracy. But a lesser-known version of this principle applies to energy and time. It dictates that for very short durations, the law of conservation of energy can be, in a sense, violated. Energy can be borrowed from the vacuum itself as long as it is repaid almost instantaneously. Special relativity, through its iconic equation E equals mc squared, tells us that energy and mass are two sides of the same coin. Combine these two principles and the vacuum transforms. It is no longer an empty stage, but the lowest possible energy state of the universe, a ground state, which in the quantum world is never truly at rest. This ground state is filled with quantum fields for every fundamental particle that exists. The uncertainty principle allows these fields to fluctuate wildly, borrowing energy from the void to momentarily create particle-antiparticle pairs, which then immediately annihilate each other, repaying the energy debt. This is the universe's ghost factory, running continuously everywhere. This constant bubbling of existence has a staggering implication, one that represents arguably the single greatest mystery in all of science. When physicists attempt to calculate the total energy density of this quantum foam by summing up the zero-point energies of all the known quantum fields, the result they get is not just large, it is catastrophically, cosmically absurd. The predicted energy density of the vacuum is 10 to the 120 times greater than the total energy density of all the matter and energy we actually observe in the universe. This chasm between theory and observation is known as the vacuum catastrophe or the cosmological constant problem. To put this number into perspective, if this theoretical energy were real and had the gravitational effect predicted by general relativity, the universe should have either collapsed into a singularity a fraction of a second after the Big Bang, crushed by its own immense energy, or it should have expanded so violently and so rapidly that no star, no galaxy, no atom could have ever formed. The fabric of space-time should have been torn to shreds. And yet, we are here. We exist in a universe that is remarkably stable, vast, and structured. The cosmic microwave background radiation, a faint afterglow from the Big Bang, shows us a universe that began in a state of incredible smoothness, allowing gravity to slowly and delicately sculpt the galaxies we see today. This presents a paradox of monumental proportions. Our best-tested theories, the very pillars of modern physics, predict a universe-destroying energy inherent in every microscopic point in space. But our telescopes show us a cosmos that is, on large scales, serene. The empty space that we perceive as placid nothingness is, according to our own rulebook, the most energetic and violent place in the universe. The very foundation of reality appears to be a raging quantum fire that, for some reason we cannot yet explain, we are completely unable to feel. How can the void itself be so wildly alive, constantly forging and unmaking the very fabric of existence, while simultaneously presenting itself as the quiet backdrop to our cosmic drama? From that bewildering dance of ephemeral particles and the paradox of their seemingly absent energy emerges a profound truth. While their collective gravitational pull appears to be neutralized, their individual effects are very much real, measurable, and consequential. The secret is not that the quantum foam doesn't exist, but that its influence manifests in far more subtle and fascinating ways. The mechanism, as we've seen, is the Heisenberg Uncertainty Principle, which acts as a kind of cosmic loophole for creation. The universe permits these fleeting energy loans, giving rise to what physicists call virtual particle-antiparticle pairs. An electron and its antimatter counterpart, the positron, can wink into existence from nothing, provided they find each other and annihilate back into nothingness within the time limit set by quantum law. They are called virtual because they exist on borrowed time and energy. They cannot be directly captured or isolated like a real particle. For decades, they were considered by many to be a mere mathematical quirk, a computational tool for particle physicists rather than a physical reality. That all changed when we discovered how to observe their shadows. The definitive proof came not from a high-energy particle collider, but from a deceptively simple thought experiment proposed in 1948 by Dutch physicist Hendrik Casimir. He imagined two perfectly conductive, uncharged metal plates placed parallel to each other in a perfect vacuum, separated by a microscopic distance. According to classical physics, nothing should happen. The plates are uncharged, and the space between them is empty. But in the quantum world, that space is not empty. It is teeming with virtual particles, specifically virtual photons of every possible wavelength. However, the space the plates acts as a resonant cavity. It physically restricts which virtual photons can exist there. Only those whose wavelengths fit a whole number of times into the gap are permitted. In the space outside the plates, there is no such restriction. Virtual photons of all wavelengths can exist. This creates an imbalance. There are more virtual photons pushing on the plates from the outside than from the inside. The result is a tiny but real attractive force pulling the plates together. This is the Casimir effect. It is a direct, macroscopic consequence of the unseen quantum foam. For nearly 50 years, it remained a theoretical curiosity, until 1997, when physicist Steve Lamoureux at the University of Washington experimentally measured the force, confirming Casimir's prediction to within 5% accuracy. The ghost factory was real. Its products could push matter. This confirmation opened the floodgates. If the quantum foam could move plates in a lab, what could it do at the most extreme frontiers of the cosmos? Stephen Hawking provided a mind-bending answer. He applied the concept of virtual particles to the event horizon of a black hole, the point of no return. He theorized that when a virtual particle-antiparticle pair is created right at this boundary, it's possible for one particle to fall into the black hole while its partner escapes. To conserve energy, the particle that falls in must be considered to have negative energy relative to the universe outside, which effectively reduces the total mass energy of the black hole. The particle that escapes carries away positive energy. To a distant observer, it appears as if the black hole is slowly radiating particles, glowing with a faint heat. This is Hawking radiation. Over unimaginable timescales, this process causes black holes to lose mass and eventually evaporate completely. The engine for this cosmic disappearance act is nothing more than the quantum foam, interacting with the warped geometry of space-time. And this brings us back to the greatest puzzle of all, the accelerating expansion of the universe. This expansion is driven by a mysterious force we call dark energy, which appears to be a small, positive energy density inherent to space itself. This sounds exactly like the vacuum energy of the quantum foam. The problem, of course, is the catastrophic 120 order of magnitude discrepancy between the theoretical prediction and the observed value. This isn't just a rounding error, it's a fundamental breakdown in our understanding. It suggests that there may be a yet unknown physical principle or symmetry, perhaps related to supersymmetry or hidden dimensions, that cancels out almost all of the vacuum's immense energy, leaving behind only the tiny residue we observe as dark energy. The quantum foam, therefore, is not a settled subject. It is the battlefield where general relativity and quantum mechanics collide. It is the source of tangible forces, the engine of black hole decay, and the holder of the key to dark energy. The nothing of empty space is the most profound and mysterious something in the entire universe.